Today, we're not just looking at a data structure. We're kind of diving into a detective story. The case file? The balanced binary tree. Our mission is to figure out what separates a healthy, stable tree from one that's, well, about to fall over. So let's start the investigation.
You know, at the heart of so many fast and efficient algorithms is this one core idea: balance. It's a lot like architecture, really. A balanced design is strong, it's stable, it's predictable. But an unbalanced one? That's just a disaster waiting to happen. A deep structural flaw that's going to cause you some major headaches.
All right, so take a look at this tree right here. I mean, at first glance, it seems okay, right? But there's a really critical flaw hiding in its structure. Something is seriously unstable here. Can you see it? This is the exact kind of problem we need our code to spot automatically.
Okay, let's put them side by side. So over on the left, you've got a healthy, balanced tree. See how everything is spread out pretty evenly? It just looks right. Now, on the right, that's our problem child. See how lopsided it is? One side is way deeper than the other. This visual difference is the key, but for a computer, we need a much stricter rule.
And that brings us to the absolute core of our investigation. The good news is, it's not some big, complicated set of laws. It's actually just one simple, elegant rule that defines the entire structure, from the very top to the very bottom.
And here is that rule. A tree is considered height balanced if, and only if, for every single node in that tree, the height of its left subtree and the height of its right subtree differ by no more than 1. That's it. Two things are absolutely crucial here. This applies to every node, and the magic number is 1. If the difference is 2, the whole thing is considered unbalanced. So how in the world do we check this rule for every single node without doing a ton of extra repetitive work? Well, the most brilliant solutions are often the most efficient. Instead of starting at the top and working our way down, we're going to flip it. We'll start at the foundation and work our way up.
This right here is the big aha moment. I mean, think about it. To calculate a tree's height, you have to visit every node. And to check if it's balanced, you also have to visit every node. The genius move here is to combine those two jobs into one single elegant pass through the tree.
So here's the game plan. We dive all the way down to the leaves of the tree first. Then, as we come back up, each node gets the heights from its children, calculates its own height, and at that exact same moment, it performs the balance check. It's incredibly efficient. But what happens if a node way down at the bottom finds a problem? How does it tell everyone else up top?
This is where our detective story gets a secret weapon, a special signal, a code that a node can use to shout up the chain of command, "Hey, stop everything. This tree is unbalanced."
I mean, just think about it. If one tiny little branch at the very bottom of the tree is unbalanced, the entire tree is unbalanced. We need a way to stop all the other useless calculations and just report the failure immediately. We need, like, an emergency broadcast system.
And this signal's only job is to travel all the way back to the root, overriding any normal height calculations. Once that signal is sent, any node that receives it doesn't ask questions, it just passes it along.
And this is our signal, the number -1. It's perfect, right? A tree's height can never be negative, so returning a -1 is a completely clear, unmistakable alarm bell. If a function returns a positive number, that's a height, everything's cool. But if it returns -1, that's a red alarm.
So here's when a node sounds that alarm. There are basically 3 triggers. 1. If its left child has already sent up a -1. 2. If its right child has already sent up a -1. Or 3. If it does the math itself and finds out its own subtrees have a height difference greater than 1. If any of those things are true, it forgets about calculating its own height and just sends a -1 up the chain. All right, theory time is over. Let's go back to our original lopsided tree and see exactly how this whole thing plays out. We're going to trace the algorithm step by step and pinpoint the exact moment the alarm goes off.
So, the algorithm dives all the way down to the deepest part of that wonky branch, and it lands on node 3. It then looks at its children, these 2 4s, which are leaves, so they each have a height of 1.
Now it's node 3's turn to do its check. The difference between its children is 1 minus 1, which is 0. 0 is definitely less than or equal to 1, so this node is balanced. It calculates its own height, which is just 1 plus the max of its children's heights, and gets 2. It sends that 2 back up to its parent. So far, so good.
Okay, now the process moves up one level to node 2. It just got the report from its left side. The height is 2. Then it looks to its right. Well, there's nothing there. It's null, so the height is 0. Now, it's time for the critical check.
And this is the moment of truth. You can see the problem laid out perfectly here. The left subtree has a height of 2, the right has a height of 0. That visual imbalance we saw earlier, the numbers are now screaming the same thing.
The absolute difference between 2 and 0 is, of course, 2. And 2 is greater than our magic number of 1. The rule has officially been broken. We found the source of the rot.
So what does node 2 do now? It doesn't even bother calculating its own height. Why would it? It immediately sounds the alarm. It returns -1 to its parent, which is the root node. The root sees that -1, knows the game is up, and the whole function can immediately return false. Case closed.
So we've seen how this pretty elegant bottom-up approach with its clever little signaling system works. But how good is it really? Let's break down the performance.
When it comes to time, the complexity is O of n, where n is just the number of nodes. This is fantastic. It basically means it's super efficient because we only have to visit each node one time. For space, it's also O of n in the worst case. If you had a tree that was just a straight line, the recursion would go n levels deep, and that's what would take up memory.
So, to wrap this all up, what are the big ideas you should walk away with? First, balance isn't just about the root of the tree. It's a rule for every single node. Second, that rule is simple. The height difference can't be more than 1. Third, checking from the bottom up is the smart, efficient way to do it. And finally, using a special signal like -1 is an awesome trick to stop work the second you know the answer. We figured out how to be a detective, right? We can spot the flaw, we can identify an unbalanced tree. But that just leads to an even more interesting question. How do you become the engineer? How would you take that broken structure and actually perform the operations needed to fix it? Well, that's a whole other investigation.